Suppose we have a parameterized curve in the xy coordinate system. This curve may be described by the parameterized functions x equals a function of the parameter t and y equals another function of the parameter t. What if we're interested in finding the length of the curve between two values of the parameter t? We will say the value t equals a and the value t equals b. Can you think of a way for us to find the length between these two values of t for this parameterized curve? Well, let's tackle this by looking at a small segment that we could approximate as a straight line. So let's say we take a segment between these 2 points. Let's identify this first point as I and this second point as I plus 1. So the first point occurs at the x-coordinate of x sub I, with the value of t being t at I. The y-coordinate of this first point is y sub I at the same value of the parameter t, t plus I. The second point takes place with an x-coordinate of x of I plus 1 at a later time identified as t at I plus 1. Similarly, the y-coordinate is y sub I plus 1 at the same value of t, t at I plus 1. We want to find the total length of this curve from points A to B. And to do this, we're going to first start off by trying to find the segment of a short straight line, because we could probably use trigonometry to help us find the value of the length of the curve. Let's take the length of this small line segment to be delta L sub I. We could use trigonometry to help us find the length. Between the I and the I plus 1 point, the change of our x-coordinate we'll define as delta x sub I, where delta x sub I is just defined to be x at the point I plus 1 minus x at the point I. Let's also take the change in the y-coordinate and identify that as delta y sub I, where delta y at the point I is equivalent to the difference between y at the point I plus 1 and y at the point I. Now, both of these changes take place in a time interval of delta t sub I, where that is the difference in time or the difference in t from the point I plus 1 and the point I. Notice we have a right triangle consisting of our straight line segments. We have the hypotenuse being equal to our tiny change of length, delta L at I. We have the horizontal leg being equal to the difference in the x-coordinate, and the vertical leg being equal to the difference in the y-coordinate. We could use Pythagorean's theorem to help us find the length of delta L at I. Pythagorean's theorem says that the hypotenuse squared is equal to the sum of the squares of the legs of the right triangle. Since both x and y are parameterized functions of t, that means this tiny segment delta L at I is also a parameterized function of t. So in order to find the length of this tiny line segment delta L at I, we should acknowledge that its length is dependent on the rate at which x and y change with respect to t. Let's reflect that relationship by dividing each of our increments, x and y, by the parameter delta t. However, if we're going to divide through by delta t sub I, we're going to need to factor that out from both terms. So in essence, we are multiplying by 1 with a delta t at I squared in the numerator and a delta t of I squared in the denominator. Using the mean value theorem, we can replace the change of x at I with respect to t at I by a derivative, the derivative of our function. So this is the derivative of f with respect to t at t sub I. And we also have the derivative of y with respect to t at t sub I using the mean value theorem. This means that the length of our line segment, delta L at I, is equal to the square root of the sum of the squares of our parameter of the derivatives of our parameterized functions f and g, representing x and y respectively, with a delta t at I outside of the integral. I need to remember that each one of these t's are evaluated at the point I. This now gives us an expression for the length of the segment of line delta L at I between the points t at I and t at I plus 1. Now what we have to do is figure out how to use this to represent the length of the overall line. In order to find the total length of this line between t equals a and t equals b, let's divide this line up into a bunch of different segments based off of the equal intervals of the parameter t. So this first interval, we might call it t at point 0, if we call a point 0, and rather let's call it t at point a. Then this one we could call maybe t at point 1, t at point 2, on and on until we cover the entire line segment from t equals a to t equals b. This means we are summing over a certain number of straight line segments. Now this sum over the straight line segments, for example, for this first point, we would call this sum, or we would call the length of this first straight line segment delta L at A. And then the second straight line segment delta L at 1. And then the third one delta L at 2, so on and so forth until we get an approximation for the length of the line being the sum of all of those different small straight line segments all the way up to the very last segment at B. This will give us a approximation for our line, but it won't necessarily give us our exact value. But at least now we have an expression for the approximation of the length of this line as being a sum over n line segments, where those line segments are given by what we found for that first line segment, which was the square root of the sum of the squares of the derivatives of our parameterized functions with respect to t. This is a Riemann sum. And from our first and second semester calculus classes, we know that if we take an infinite number of small segments of intervals delta t, so in other words, if we take n going to infinity of our sum, what do you think we'll get? Well, the limit as n goes to infinity of our sum of these line segments from the first segment to the nth segment equals the definite integral from a to b of the square root of the squares of the derivatives of our functions with respect to the parameter t. This will give us the value for the length of our line between points A and B. We could even generalize this to 3 dimensions. If we had a coordinate system were described by x, y, and z, and if we had functions, we could even generalize this to 3-dimensional space by adding a third parameterized function representing the z coordinate. Let's call this third parameterized function h. And this would just be the addition of the derivative of that parameterized function h to our integral, where again we are defining x is a parameterized function f of t, y is a parameterized function g of t, and z is a parameterized function h of t on the interval of a to b. This is our expression for the length of a curve between 2 points.